Good afternoon. Welcome to the last session, actually, the last problem solving session of this course. It is a 1 hour session from 3 to 4 p.m. and after this, you have the exam on 29th of October. So, let's start. So, the course instructor is Professor Bhanu Prakash Velanki from Department of Civil Engineering, IIT Roorkee. And I am Asma Parveen. I am a PhD scholar at Civil Engineering Department, IIT Kanpur. So this is which was overall topics which was discussed in this course. So the week one was about thermodynamics, and also some of the fundamentals for kinetics was also introduced in week one. In week one, there was about Gibbs free energy. Lectures was about Gibbs free energy. Then week two was about component balance, reaction kinetics, and mass balance was also introduced in week two. Week three was about material balance, that is mass balance, and acid base reaction was also introduced in week three. Week four was a week four, and week five was about acid base like log CPH graph, titration, buffer intensity, alkalinity, acidity, and so on. Then week 7 was also about acidity and alkalinity, and it was also about mixing of two solutions. What are the conservative quantities? What are non-conservative quantity? And week 8 was about aqueous complexes and also precipitation and dissolution. Week 9 was also follow-up of that. There was application of precipitation and dissolution, equilibrium for this, and some examples was also discussed. Then week 10 was about solubility and competitive precipitation, whether the solid will precipitate out or not. Then it was about if more than one solid is precipitating, then what are the solids which will precipitate out at different pH. Also, week 10 was about predominance area diagram, and introduction to redox reaction was given in week 10. And week 11 and 12 was about redox reaction, its applications, and its kinetic, equilibrium of redox, its reaction feasibility, followed by real scenario in which redox along with other phenomena like precipitation, dissolution are taking place. And in that case, we have seen how to solve the problem related to redox reaction. So this was all about all the 12 weeks. Now what we will do, we will try to solve one or two. We'll try to solve, I think, 5, 7 or 6 numericals based on, I have taken some random topics like pH or precipitation, and then we will try to solve the questions. So let me go to the question. So this question is about this question is for very basic question in which we have to find out the concentration in milligrams per liter, and it is given in milliequivalents per liter. So the question is, a solution is reported to have a total hardness of 4.5 milliequivalent per liter. If 80% of the hardness is contributed by calcium and other 20% by magnesium, what are the concentration of calcium and magnesium in milligrams per liter? So we have been given the hardness, that is total hardness, and it is given that it is due to calcium, and around 80% is due to calcium and 20% is due to magnesium. And we have to simply convert the concentration from milliequivalents per liter to milligrams per liter. So we have seen this type of question, I think, in week 1 or week 2 assignment questions. So let's see. So we have been given total hardness. It is 4.5 milliequivalent per liter. and hardness due to calcium is 80%, that is 0.8 into 4.5, that is 3.6 milliequivalents per liter. And hardness due to magnesium is 20%, that is 0.2 into 4.5, 0.9 milliequivalents per liter. And now we have find out how much hardness is due to calcium and magnesium. Now we have to simply convert the milliequivalents into milligrams per liter. So we know that equivalent weight of calcium is equals to molecular weight, or it is for an atom, so we'll write atomic weight upon Z, where Z can be charge, or it can be number of H plus, or it can be number of electrons transferred. So we know that atomic weight of calcium is 40 and charge on calcium is 2. So equivalent weight of calcium is 20 grams per milliequivalent. Sorry, it will be grams per equivalent. We can convert it to milligrams, so it will be 20 milligrams per milliequivalent. Similarly, we will find out equivalent weight of magnesium. So we know that atomic weight of magnesium is around 24. So 24, and again charge on magnesium is 2. So it will be 12 milligrams per milliequivalent. Now let's find out concentration of Ca2 plus is 3.6 milliequivalent per liter, and we have calculated the equivalent weight of calcium as 20 milligrams per milliequivalent. So it is 20 into 3.6, that is 72 milligrams per liter. Similarly, we can find out concentration of magnesium as 0.9 milliequivalent per liter into equivalent weight is 12 milligram per milliequivalent. So it is overall 10.8 milligrams per liter. So we can see that it was a simple question based on conversion of milliequivalents to milligrams per liter. So let's go to the next question. So this question is based on the material balance or mass balance in any system. So the question is, a stream containing 25 milligrams per liter of bromide concentration flows to a lake with a flow rate of 40 meter cube per second. Another stream having 60 milligrams per liter bromide concentration and 5 meter cube per second flows into the lake. Considering the lake as a controlled volume, bromide as a conservative substance, and complete mixing in the lake, calculate bromide concentration in the stream which flows out from the lake. So we have been given that two streams are flowing into a lake, and we have to find out the final concentration of the pollutant which will come out from the lake. So let's first draw the figure for this question. So suppose this is some lake, and here stream 1 is flowing into this. So this is stream 1. The concentration of bromide here is 25 milligrams per liter. And here the flow is, that is Q1 is 40 meter cube per second. and there is one more stream. Let it be stream 2. So the concentration of bromide here is 60 milligrams per liter and flow is 5 meter cubes per second. Now suppose this stream is coming out and we have to find out what will be the concentration of bromide in the water coming out of this lake. So let's first write the equation for material balance. As we know, net accumulation equals to mass flow in, minus mass flow out plus summation of source, or you can write generation minus sink. So we will also consider it is a complete mix. It is given that bromide concentration is bromide is conservative substance. It means it will not react with anything. It will be like that only, and it will come out in the outflow. And there is complete mixing in the lake, so the concentration will be same everywhere. So we have to find the concentration in the coming water. Since the bromide is a conservative substance, so it will not be accumulated. The lake will always be in the steady state. So net accumulation will be 0. So if we see the mass flow in, then we can see the first stream. It is flow is Q1, concentration is C1. The next stream is Q2, C2. Minus, we have to find out the mass flow out. So the flow rate will be Q1 plus Q2, and let us assume the concentration coming out to be C. And since it is conservative, so there will be no generation and sink, so it will be 0. Also, one thing we have to note that the unit in which this mass flow in will be everything net accumulation, it will be kg or milligrams per second. So let's see, we have Q1 as meter cube per second, into we have concentration as milligrams per liter. So these two are the units of volume. So finally we will get milligrams per second. So let me rub this. Okay. So we have to find out C. Let's simplify this. C will be I don't know why the mark is. So C will be Q1 C1 plus Q2 C2 upon Q1 plus Q2. So we have Q1 as 40, C1 as 25, Q2 as 5, and C2 as 60 upon Q1 plus Q2, that is 40 plus 5. So after solving this, we will get C as 28.89 milligrams per liter. So this question was based on mass balance in any lake system. Two streams were coming in with some concentration of bromide, and we were about to find out what will be the concentration of bromide in the outflowing stream. So let's move to the next question. So this question is based on thermodynamics. We have been given that the question says the conversion of Fe2 plus to Fe3 plus by reaction with dissolved oxygen can be represented by the following reaction, which has an equilibrium constant of this. So we have been given the reaction along with the equilibrium constant. K is 2.95 into 10 raised to 8. A solution at pH 6.8 contains 2 milligrams per liter of Fe2 plus, 0.01 milligrams per liter of Fe3 plus, and zero point 0.1 milligrams per liter of oxygen aqueous. If all the solutes behave ideally, in which direction will the reaction proceed? Is it reasonable to treat the reaction as irreversible? So we have to find out whether the reaction will proceed in the forward direction or backward direction, and whether the reaction can be treated as irreversible or not. So we will find out the reaction quotient at the given concentration of the reactant and products. So we have been given the concentration in milligrams per liter, and as we know, we need to convert these into number of moles per liter, because the concentration we take in the reaction quotient is in terms of moles per liter. So let's first convert Fe2 plus as 2 milligrams per liter to number of moles per liter. So it will be 2 into 10 raised to minus 3 grams upon molecular weight of iron is, I think, 56 grams per mole. It will be grams per liter. So overall, let me calculate this. So after calculating this, we are getting Fe2 plus as 3.57 into 10 raised power minus 5 m. M is moles per liter. And after converting Fe3 plus, it is 0.01 milligrams per liter. Similarly, it will be 0.01 to 10 raised per 3 upon atomic mass, that is 56. So we are getting Fe3 plus as 1.79 into 10 raised per minus 7 m. And last one is O2 aqueous, which is 0.1 milligrams per liter per liter. So it will be 0.1 into 10 raised per minus 3 upon 32. So it will be 3.13 into 10 raised per minus 6 m. So let's find out the reaction quotient. So sorry, Q will be, on the product side we have Fe3 plus activity of Fe3 plus, it will be into activity of H2O raised to the power of 0.5 upon activity of Fe2 plus into activity of O2 aqueous raised to the power of 0.25 into activity of H plus. So it is not given, so the concentration is also very less, so we will assume the system to be diluted and the concentration activity will be equivalent to concentration. So let's go to next page. So Q will be Fe3 plus, and also we know that activity of H2O is 1. So we have already calculated these in the previous slide, so we just have to put everything here. And also some pH was mentioned in the question. Let's see what was the pH. The pH of the solution is at 6.8. So concentration of H plus will be 10 raised to power minus 6.8. So after solving this, we are getting Q as 7.50 into 10 raised to power 5. Also K was given as 2.95 into 10 raised to power 8. So we can see that K is greater than Q. So K is greater than Q. So the reaction will move in the forward direction. It means it will go towards formation of products. Also there was second part in the question. It was given that whether we can treat is it reasonable to treat the reaction as irreversible. So let's find out what is the ratio of Q by K. So Q is 7.50 into 10 raised to minus 10 raised to 5 and K is 2.95 into 10 raised to 8. So after solving this, we are getting Q by K as 0.0025. So we can see that the ratio of Q by K is much lesser than 1. So we can treat this reaction as irreversible. So in the question it was concentration of all the species was given, and we have to find out the reaction quotient and compare the reaction quotient with the activity with the equilibrium constant, and if it is greater than the equilibrium constant, it means the reaction will move in the backward direction to reach the equilibrium, and and if it is less than the equilibrium constant, then the reaction will move in the forward direction to move towards equilibrium. Also, the ratio of Q by K tells whether the reaction is very much nearer to equilibrium or it is far away from the equilibrium. So in this we have seen that the ratio of Q by K is very less than 1. So we can treat the reaction as irreversible. So let's move to the next question. So the question is, a natural water has a dissolved organic carbon concentration of 3.5 milligrams per liter. The average composition of the organic molecules in the solution is this. This is the average composition of the solution molecules is given. Assuming that all the molecules actually have that composition, compute the molar concentration and mass concentration of molecules in the sample. So we have been given the dissolved organic carbon concentration and also we have been given the formula of the molecular formula of the molecule, and we have to find out what will be the concentration of that molecule in molar and also in mass term. So it is also a simple question based on conversion of a unit from milligrams per liter to molar concentration. So let's see how to solve this question. So the dissolved organic concentration, it is 3.5 milligrams per liter, and the molecule for molecule composition is C30H33O18N. So its molecular weight will be, molecular mass or weight will be, so we have 30 carbons, so 30 into atomic mass of carbon, that is 12. We have 33 hydrogen, so 33 into atomic mass of hydrogen 1, 18 oxygen into atomic mass 16 plus 1 nitrogen into atomic mass 14. So after solving this, we are getting 695 grams per mole. So this is the molecular weight of the molecule. Now we can solve this question simply by unitary method. So we know that from this molecular formula, we know that in one molecule there is 30 carbon atom. So in 1 mole there is 30 moles of carbon atom, that is in 695 grams we have 12 into 30 grams of carbon. So we can reverse this statement. It will be 12 into, for 12 into 30 grams of carbon, or we should write dissolved organic carbon. We need 695 gram of C30H33O18. So for 1 gram we can simply find out it will be 695 by 12 into 30, and in the question it was given as 3.5 milligrams per liter of dissolved organic carbon is there. So it will be equivalent to 695 by 12 into 30 into 3.5. So after solving this, it is around 6.757 milligrams per liter. Now this is the concentration of mass concentration of the molecule. Mass concentration of the molecule it is 6.757 milligrams per liter. Now also we have to find out the molar concentration. So we have been already given the mass, that is 6.757. We have calculated the molecular mass, that is 695. So to convert into milligrams, sorry, so it will be 9.7223 micromolars. So this is the mass concentration and molar concentration of the molecule. So this question was also a simple question in which we just have to convert the uh, carbon concentration to the overall molecule concentration and find out the molar and mass concentration. So let's move to the next question. So it is also a direct question. We have to compute the ionic strength of the solution containing A is 0.05 moles per liter of NaCl. Next is this much mole of sodium sulfate and magnesium sulfate. All these salts dissociate completely, so the resulting solutions containing only these cation and anion in addition to H2O. So there are no additional cation and anion except these which is mentioned in the question. So we know that ionic strength it is given as half Ci into Zi square, where Ci is the concentration and Zi is the charge of the cation on anion. So let's find out for 0.05 moles per liter of NaCl. So ionic strength will be half. So concentration of Na will be 0.05 into charge will be 1 plus square. Again Cl will be 0.05 into minus 1 square. So after solving this, we will get the ionic strength as 0.05 m. Similarly for B, ionic strength will be, so let me write here only that NaCl will dissociate in Na plus Cl minus, and by sodium sulfate it will dissociate into Na plus and SO4 2 minus, and MgSO4 will dissociate as Mg2 plus and SO4 2 minus. So for the second question, ionic strength will be half, concentration is 0.025, but we have 2 moles of sodium, so into 2 into charge on sodium is plus 1, so plus 1 square. Again sulfate is only 1, so it will be 0.025, but charge on sulfate is minus 2, so minus 2 square. So after solving this, We are getting the ionic strength as 0.075 m. So next is for MgSO4. So half into concentration is 0.025. Charge of magnesium is +2, so +2 whole square, plus sulfate concentration is 0.025 into -2 square. So it is coming out to be 0.1 molars. So this is a simple question based on calculation of ionic strength. If you remember what is the formula for ionic strength, then we can simply find out the ionic strength. So let's move to the next question. So here it is given that compute the Gibbs energy change when 15 micromoles of atmospheric CO2 at a partial pressure of this combines with water to form 30 micromolars of H plus and 15 micromoles of carbonate, which are present at concentration of this and this respectively in a system at 25 degrees centigrade. The reaction and the standard Gibbs energy of formation of the constituents are given as follows. So we have been given the concentration of the constituent along with the Gibbs free energy of formation. Assume that the solution is ideal, that is activity coefficient R1, and that the solution volume is large enough that this amount of reaction does not change the concentration of dissolved H plus and carbonate significantly. Is the system thermodynamically favorable? So we have to simply find out whether the system will be thermodynamically favorable or not. So to find out whether the system will be thermodynamically favorable or not, we will find out the Gibbs energy for the overall reaction. So we know that first find out the Gibbs energy at the standard conditions, that is 25 degrees centigrades. So delta G naught will be summation of the Gibbs free energy of the constituent on the product side minus summation of the reactant side. So we have been given 2 times into delta G naught of not be G naught of formation of H plus G naught of formation of carbonate minus Gibbs free energy of formation of CO2 plus Gibbs free energy of formation of H2O. So this will be our overall Gibbs free energy at standard condition. So we have been given that just we have to put out the values. So after calculating, we are getting delta G naught as 103.65 kilojoules per mole. So we know that it is at equilibrium. When the reaction is at equilibrium, this will be the delta G naught, but the reaction is not at equilibrium. So to find out the Gibbs energy of formation at any other condition, we know that we use this formula, that delta G is equal to delta G naught plus RT ln Q. Q will be reaction quotient, so delta G naught plus RT ln activity of H plus, it was given in the question that the activity coefficient is 1. So activity will be equal to the concentration into CO3 upon CO2. So since the CO2 is in gaseous form, so we will take partial pressure of CO2 plus we know that activity of H2O is 1, so it will be 1. So delta G naught we just have calculated as 103.65 kilojoules per mole plus R, it will be 8.314 into 10 raised per minus 3 kilojoules per Kelvin per mole, and temperature we will take as Kelvin. So it was temperature was 25 degrees centigrade. So plus 25 plus 273, it will be 298 Kelvin. So into 298 into ln, the concentration of H plus was given as 10 raised per minus 2. Coefficient is 2, so square into 10 raised per minus 4 for carbonate. Partial pressure was 3 into 10 raised per minus 4. So after solving, we are getting so it is minus 24.58 kilojoules per mole. So I think this was the question that we have to find out, is the reaction thermodynamically favorable. So we can see that yes, the reaction is thermodynamically favorable because the Gibbs free energy is negative. Also we can see on the first line that we have to compute the Gibbs free energy change, that how much energy will be changed when 15 micromoles of atmospheric CO2, it is combining with water to form 30 micromoles of H plus. So we can see that 1 mole of CO2 is forming 1 mole is forming 2H plus. So 15 micromoles is given as 30 micromoles will form 30 micromoles of H plus. So the Gibbs free energy change Gibbs energy change will be equal to the Gibbs free energy which we have calculated just now, this one, into number of moles change in number of moles of the reaction. So it is minus 24.58 into 10 raised per 3. It is joule per mole, and number of moles involved is 15 micromoles. So 15 into 10 raised per minus 6. So after solving this, we will get Gibbs free energy changes minus 3.687 into 10 raised per minus 4 kilojoules. So the first part was to find out the Gibbs free energy change. So this is the Gibbs free energy change. And the second part was whether the reaction is feasible. So the reaction is feasible because we know if the Gibbs free energy change is negative, that is Gibbs free energy is negative, so reaction is feasible. So this is the last question. So question is, the process of softening water is by inducing the precipitation of calcite. Typically, softening involves addition of lime to increase the solution pH, and in some cases of sodium carbonate to increase total carbonate. Historically, lime and soda ash doses were often chosen based on a target of stoichiometric softening, meaning that the dose were chosen so that total calcium is equals to total carbonate. Consider a solution that has been subjected to stoichiometric softening and has a final pH of 10.5. If the solution has reached equilibrium with calcite, what is the concentration of dissolved calcium? And second part is, if the sum of Ca2 plus in the original solution and that added with lime is this much, how much calcite is generated per liter of water treated? So this question and all the previous questions have been taken from the book Water Chemistry by Benjamin. So you can also refer to the book. So let's see how to solve this question. So we have been given the pH is 10.8 and we are precipitating out CO3 solid, so it will dissolve as Ca2 plus and CO3 2 minus. So during softening, we decide the dose, we choose the dose at which the total calcium is equal to total carbonate. So first part is we have to find out the concentration of dissolved calcium. So also we know from the standard tables, we know that Ks naught for this reaction is 10 raised to power minus 8.48. So Ks naught will be Ca2 plus into carbonate. We can write carbonate in the terms of alpha 2. That will be the coefficient at a particular pH into CO3 total upon activity of calcium carbonate will be 1. So also we know that alpha naught, alpha 1 and alpha 2, these depend upon the K1 and K2 and the pH of the solution. So H plus, that is H square K1 H plus K2 K1 KO2. So we know that H2CO3 dissociates as H plus and HCO3 minus, and Ka1 is 10 raised to minus 6.35. And again this HCO3 minus dissociates as H plus and CO3 2 minus, and Ka2 is 10 raised to minus 10.33. So after putting the value of Ka1, Ka2 and pH is 10.8, that is H plus will be 10 raised to minus 10.8. We can find out the coefficient, we can find out the alpha 2 and we can put in this equation. So the concentration of calcium will be Ca2 plus will be equal to so we know the total calcium will equal to the Ca2 plus concentration that will be dissolved plus plus it will be summation of the hydroxide complexes of calcium. But calcium makes only one complex, that is CaOH, and it forms at pH greater than 12. I think the pH is around 12.6 or 12.8. So we can discard this form of calcium and also we can write that total calcium Ca2 plus total, it will be equal to Ca2 plus. Okay. So let's go to the next slide. So we can write Ks naught now as Ca2 plus, that is Ca2 plus total is equal to Ca2 plus into alpha 2 into CO3 total. And just now we have read the statement that softening is done till Ca2 plus total is equal to CO3 total. So Ca2 plus can also be written as Ca total. So we can write Ca2 plus square equals to Ks naught by alpha 2, or we can write Ca2 plus as under root of Ks naught by alpha 2. So after solving this, we will find out the value of alpha 2 from the previous formula, and we will find out total calcium as, sorry, dissolved calcium as 6.69 into 10 raised to power minus 5 m. So I think this was the first question. So what is the concentration of dissolved calcium? So this much is the, that is 6.69 into 10 raised to power minus 5 molar is the dissolved calcium. And next part is, if sum of calcium in the original solution and that added with the lime is 180 milligrams per liter. So total calcium concentration is given as 180 milligrams per liter, and we have to find out how much calcite is generated, that is CuCO3 is generated per liter of water treated. So let's find out total calcium. It is 180 milligrams per liter. So let's convert it into molars. So it will be 180 into 10 raised to power minus 3 by mass of calcium, it is 40. So it will be 4.5 into 10 raised to power minus 3 m. So this is the total calcium which is added in the system. That is the sum of calcium in the original soil system and that added with the lime, and we have to find out how much calcite is generated. So here we can see that for making 1 mole of calcium carbonate, that is calcite, 1 mole of calcium is required. So if 1 mole of calcium carbonate will be formed, 1 mole of calcium will be removed from the dissolved form to the and converted to the solid form. So if we want to know how much calcite it formed, then we need to know how much calcium has been converted from the dissolved to solid form. So we can find out calcite generated as difference between total calcium minus dissolved calcium. So total calcium is 4.5 into 10 raised to power minus 5, and dissolved calcium which we have calculated in the previous question. So it is coming out to be, okay, we can convert directly into milligrams per liter by multiplying it with 100, because the molecular mass of calcium carbonate is 100 grams per mole. So also to convert it into milligrams, we will multiply again by 1000, and finally we will get calcite generated as 443.3 milligrams per liter. So this is the final answer, that is the concentration. We have calculated the concentration of dissolved calcium, and also we have calculated how much calcite is generated per liter of water treated, that is 443 milligrams per liter. So thank you so much for joining. Have a nice day and all the best for your exams.